What does degrees of freedom mean?
Okay, so basically degrees of freedom is the number of observation minus one for one
Uh,
simple test.
Wait, which one are you reading?
I'm just trying to understand the concept. Number of observation minus one for certain test.
For one simple test. So far all of the tests are one simple test. So you just find out how many data points you have. That is the number of observation, and use that minus one is your degrees of freedom.
What is that on the PowerPoint?
It's called DF. So I believe in the PowerPoint they just use abbreviation. The DF stands for degrees of freedom.
Yeah.
That is very useful when you want to find the T critical value, right? Remember when you go to the T table, you should have two important parameters. The first one is the degrees of freedom, right? So every time you go to a T table, you have to know the degrees of freedom in order to get a critical T number.
Okay. Hold on, I gotta find a pen.
Okay. And then what is alpha again?
Alpha.
The level of significance.
Okay.
That is that has something to do with your confidence interval, right? So anytime you want to reject a null hypothesis, it doesn't mean that you are 100% sure that the null hypothesis is wrong, but instead, for many times, we would say we reject the null hypothesis at alpha equals 5%. That means I am 95% sure that this null hypothesis is wrong. So, because there's always uncertainty in statistics, and
So alpha, sorry, go ahead.
yeah, in this class, many times we use alpha equals 5% or 10%. That means I will reject the null hypothesis if I'm more confident than 95% or 90%. Right, so every time when you go to a T table, you need first the degrees of freedom and second the alpha, right? And in this class, we will give you the alpha in every question, and normally it is 5% or 10%. So with the degrees of freedom and with the value of alpha, you can find the T critical value on the table.
Okay, so alpha is the confidence level.
It has something to do with the confidence level, but it doesn't have like a meaning like in terms of natural language. You just remember that is alpha, and when alpha equals 0, that means I am 100% sure that I can reject the null hypothesis. But in reality, there's always uncertainty. I'm not 100% sure of anything. So we will use this alpha as a term of uncertainty, right? So basically, if alpha is less or equals to 5% in this class, you will likely reject the null hypothesis.
So if you do just conceptually, right? If you do a set of trials, let's say 100, the degrees of freedom would be 99.
Yep.
And then your mean that you have in those trials, I think the point is that there's a mean for those because that's a sample, but then that 100 is a component of an infinite amount of trials in theory.
Yep.
And so the mean of the entire infinite possibilities could be different or could be very similar to the mean of the 100 trials, and your alpha is saying, I'm 95% or 90% confident that the mean of the 100 is in line with the mean of the entire infinity. Is that right?
It's close. It's very close. So here's the argument. You said you have 100 trials, right? And actually, as the number grows, instead of 100, maybe I have 1,000, I have 10,000 trials, then the mean of my sample will be closer and closer to the actual mean of the population. Does that make sense?
Yes.
As I have more and more observations. Yes. So basically, it doesn't mean we are confident that the sample mean is equal to the population mean, but instead, um, I want to test if my sample. So basically, we assume the population mean is equal to the sample mean. That is the assumption here. And then, because we cannot test every single statistics, so our best approach is to find as many samples as possible, and we calculate that sample mean as our population mean. That is the assumption here. And then sometimes we want to know if the population mean is likely to be some arbitrary number. Then we should do a t-test. And our t-test, you know the formula. We use the sample mean minus that arbitrary number we want to test and divide it by the standard error, which is our calculated t. And we compare that with the t-critical value. So basically the alpha and the confidence interval is how confident we are to say that our sample mean is, or our population mean, because it's the same in this case, we assume they are the same. So our population mean is different from an arbitrary number we want to test. This is basically the rationale of the t-test.
Okay. Can we look at the first problem?
Okay, sure.
So, in a study in nuclear fuel waste management, researchers discover that when oxygen is inserted in molten salt at a sparing rate of 3.3 x, how do you say that? 3.3 times 10 to the negative 6 power?
Yeah, maybe. Yeah, but I
Okay.
think that the number is not so relevant.
Okay. That the true mean, yeah, the true mean bubble rising velocity is mu equals 0.338. In the routine monitoring of the process, inspectors measured the bubble rising velocities at 25 different points in time. The data is given in the table below. So part A, conduct a test of hypothesis to determine if the true rising velocity for a population from which the sample is selected is mu equals 0.338. Use alpha 0.10. Okay. So how do you do that without putting it all into a calculator?
So first, you're gonna find the mean and standard deviation of that 25 observations, right?
Okay.
In the chart, like there's 25 observations, and you need to find the mean and the standard deviation of those data set. And then I have already said there is like an arbitrary number that we want to test if that could be the actual mean. And in this case, that is mu equals 0.338. That is something we want to test. Could that be the actual mean of the population? Therefore, we should conduct a t-test.
So in this case, we're doing like each individual one by itself, right? Like we're adding all of these together and finding the mean of this sample.
Yep.
Okay. That'll take a minute. Okay. So, okay. 270.
Remember, this is always a formula of how to calculate a t, right? You use the difference between the mean. Here, the x bar is the mean of this 25 observations, right? And the mu is something we want to test. In this case, mu is 0.338, and we divide it by the standard error. That is the standard deviation of those 25 observations divided by square root of 25, right? This n equals 25, capital N equals 25. And the standard error, that's the thing in the denominator, sigma divided by square root of n. We call that the standard error. It is just an adjusted standard deviation because we need to use the standard deviation scaled by the number of observations. The more observations we have, we will get a smaller standard error and therefore a greater t because that is in the denominator.
So X bar is the mean of a t-test, you said?
Is the mean of those 25 observations I have.
I'm doing it by hand.
Yeah,
Okay.
I mean, you can do it. You can do whatever you want. I think the most easy way is you just copy paste these 25 numbers to a statistics calculator, or you just Google statistical calculator or something, and you copy paste those 25 observations, and they can immediately gives you the mean and the standard deviation, which is the x bar and the sigma in the
Okay.
formula.
So X bar is, because I put in the calculator, X bar is 0.26208.
26208. I got that too if I added them all together and divided by 25.
Okay. And then which one is the standard deviation? SX?
So we do
Sample standard deviation. I'm looking at my calculator.
Yeah.
S
sample
S
standard
sub X is 0.046691291.
how did you do that?
I put it in this handy dandy calculator. But
Basically,
you can do
that's
it.
the residual squared divided by n minus 1. That's the formula for standard deviation. So if you're doing that by hand, first you calculate the x bar, right? That is the mean. And you use each of those individual data set minus the x bar and square them. That is the square root of that is the square of residual. So you use point.
So the first one you would
275.
do 0.275 minus 0.262 squared.
And you add them up. You add 25 observations up, right?
Mm-hmm.
Because there's 25 set of data, and then you divide it by 24. I guess that is the formula of how you calculate the standard deviation. This is the variance, and you should square root that. You get the standard deviation. I believe that is a formula. You should check your notes. I think it's covered in the first several classes.
Okay.
And
Quick side question.
where did you put them in, Paloma? Like which part of the calculator?
Yeah, it's in if you go to stat, and then you go to test, and then number 2 is t-test, enter. And then it says input data, enter. Wait, hold on, I skipped the part.
Can that be done by hand?
I think maybe.
Can you do it by hand?
No, I can't.
Okay, so
That's what I was
then,
gonna ask, like, are we, if we just like had this calculator and we just plugged it in here, like how much information are you looking to see on the, handwritten information work are you looking to see on the final?
I mean, the more you provide, the more partial credits you could get. So my principle is if you get the answer right, you will be very likely get a full marks, get 100% grade. Um, but in case you get the final answer wrong, I would suggest you like provide as much process as possible. Maybe you can even write on how you get the standard deviation using your calculator. And in case you get a wrong answer, you still get partial credits by that.
Okay. Olivia, it's stat. You go to the stat button and then you go to list. And then you input all of those, the 25 data points. And then you press stat again, and then you go to tests, and then it's t-test. And then you change the mu sub 0 to whatever the null hypothesis. So in this case, it's the 0.338.
And for Oliver, I think if you don't have like a statistical calculator, what I'm doing that is I will Google statistical calculator and click on the first link. And
I have a calculator, and I was going to Google it as well because I didn't feel like getting to go get the calculator. I was more just curious about the, like, what we're expected to be able to do by hand on the final without a calculator and without a computer, and what you're expecting to see on the homework in terms of how much work we show, which Paloma asked. I'm just more curious about like those components. Right? A calculator is nice,
Sure.
right? And like it's probably more representative of the real world because we will always have access to it. But as it relates to the being graded, it won't be available.
Definitely, you won't calculate like each residual squared and add them up. No, even in the homework, no. You should use some software or calculator to do that. But you could actually provide more rationale. For example, you just said I put those numbers in a calculator to calculate the sample standard deviation, something.
Mm-hmm.
Yeah, just so I can.
So I wrote down like, oh, I went to. Sorry.
Yeah. So just so I can see you're not directly copying others' answer.
Okay. Okay. So yeah, the calculator is easier than doing all of those formulas by hand. It's actually crazy. Okay.
Okay, what number do you get, Paloma? Just so we can keep for deviation.
I got 0.0466912911.
Okay. So that means that our mean for the sample was the 0.262. Our standard deviation for the sample is 0.466. So then what is the question? Well, okay. Conduct a test and determine if the true rising velocity for a population is 0.388. So then we have to apply the confidence interval, right?
Yeah, like for this question, you're not using the confidence interval, but because you're not go that far during the last lecture. So first for part A, you have your calculated t, right? And then you should find what is the critical number of t, the t critical number, critical value actually, and the notation would be TCV, and you should look that in the t table, right? Every time, um, I guess like you should have a t table on the back of your back few pages of your textbook, or you can Google a standard t distribution, a t table. Right? To find a t critical value, there's two parameters you have to know. The first is the degrees of freedom, and you already know that's 24. It's n minus 1. And then you need to have an alpha. And in this case, alpha equals 0.1, but that is a two-tailed test. So in each tail, the alpha would be 0.05. That is something a little bit weird, I would say, but I would not deducting a lot of points by like alpha equals 0.1 or 0.05, but just like in this question, the alpha equals 0.05.
How do you tell the difference when you're reading a question if it's a one tail or a two tail test?
Okay, so that is the difference between the two home assignment in this, between the two questions in this home assignment. It's like it has something to do with your null hypothesis and alternative hypothesis, right? In this case, my null hypothesis would be mu equals 0.338. That's something I want to reject, right?
Mm-hmm.
And my alternative hypothesis is mu not equals to 0.338, right?
Mm-hmm.
Because at the first glance of those 25 data sets, I have no clue of what is my mean, right? You guys have already calculated this x bar, and you get something like 0.2 something, right? And you would say that is smaller than the mu, than this thing we want to test. But at the first glance of those data sets, I have no clue, and I don't have any preference. I don't care if the mean is greater or smaller than the mu 0.338. So it becomes a two-tailed test. Our like population mean could either less than 0.338 or greater than 0.338. And like this is a t distribution, right? It's still a symmetric distribution, and there's two tails. But after you find x is smaller than mu, you want to reject this null hypothesis by proving the population mean is less than 0.338. So you only have this left tail. So you should divide your alpha by 2, and you get the one-tailed alpha is 0.05. And again, a two-tailed test or one-tailed test really varies in different problem sets, in different situation. So it's something matters, but I don't think it's very important. Okay, so you just need to know that you need to find the degrees of freedom and the alpha in order to get the t critical value, and you find your t critical value in the table.
Okay. And then, sorry, can you just repeat again, what's the degree of freedom? It's 1 minus what?
It's n minus 1, the number of observation minus 1.
Okay.
And then how did you find so I understand how you got the standard deviation. I understand how you got the mean. How did you get the t value?
You just use this formula here.
So the value equals the mean of the sample minus the mean of the population. divided by,
like this mu is not the mean of the population. It's something we want to test. Could it be possible that the mean of population is mu? And this is, we just have the null hypothesis here. It's not the actual mean of population. It's just our hypothesis.
Mhm.
And actually, it's something we want to reject.
and it's over the standard deviation divided by the square root of n.
Yes. You can see that formula in the slides, the PowerPoint of the lecture.
So that would literally be 0.262 minus the 0.338 over the 0.466 square. What is n in this case? The number of trials?
Yep.
Mhm.
Okay. So this will give us a number.
Yes. And you should compare that number with the t-critical value
Where's the t critical value?
on the t-table.
This is very confusing, my friend.
Okay. Let's do this. You can find the t-table on the
Yeah,
last few pages of your textbook, but I just Googled that.
All right, so if I get -8, that's a big number.
Yeah, that's a big number, definitely.
For the T. For the
Well,
T, Olivia?
That's what I got for T. Does that make sense for you?
Yeah, that's what I got on my calculator.
This
Like,
is, yeah. Like, can you see this green, a t-table? Like I said, you have to find on the top left corner, it's a DF. You get that DF. That is standard deviation. And beside it, it says A equals 0.1, 0.05, something. That A stands for alpha. So every time you have horizontal value, you have your alpha, and a vertical value, you have a degrees of freedom. You can locate to a coordinate that gives you the critical t value, right? In this case, you want to find the alpha equals 0.05. So that's in the third column of this table, alpha equals 0.05. And then you go down until you find the degrees of freedom equals 24. And you can get your t critical value.
But so in the back of the book, oh, I got it.
Yeah. Every time you should have a degrees of freedom and an alpha. You have those two parameters. You can get a coordinate of a single value. That is your critical value of t.
So the T value would be 1.711.
Yeah, it seems to me. Yes,
Would that be negative or positive?
it's always positive. When you calculate your t value, I'll stop sharing this and share the homework. When you calculate the t value, you will always want to find the absolute value of t. And the reason of it is the t distribution is symmetric, and it doesn't matter a negative one or a positive one. So by putting an absolute notation here, you will always get a positive t value. And the answer stays the same, no matter it's -2 or +2. The answer stays the same.
So what is that T value versus the 8 telling us? So the T bar is 1.711. The T of the sample is -8.
So basically, first you should convert that -8 to a +8. Okay, because that doesn't influence the final answer, but in the t table there's only positive value, right?
Okay.
Since the t distribution is symmetric, so +8 and -8 are essentially the same.
Okay.
So what tells you is like this is a standard t distribution. There's a t distribution. And your calculate t is 8 point something. I would say here. I have like a vertical line here. T equals 8 something.
Yep.
And our alpha equals, when alpha equals 0.5, the t value is your t critical value. When degrees of freedom equals 24. So here, maybe there, what you find is maybe 1.7 something. This is your critical t value. That gives you alpha equals 0.05. What does that mean? That means the shaded area on the left, the shaded area is 0.95 in this case. And the white area is 0.05. And the area stands for probability because the whole area equals 1. So my probability of population mu lies in left area is 95%, while in the right area is only 5%. And our tested sample mean 0.338 actually gives us a t-value of 8. That is very, very left, very, very right to this distribution. So the probability of getting a mu equals 0.338 would be very, very small, smaller than 5%. So that's why we reject that.
Because if you do 1.7 plus 3 standard deviations to the right, 3 standard deviations gets you like 99% there, then your number is 1.82. So the point is that if the z, right, or do you apply it to the, do you apply the standard deviation to the mu or to the z?
To the z, right? In the z score test, sometimes we see it's 4 standard deviation above the mean, it's 3 standard deviation below the mean something. But in the t-test, what really matters is the relative relationship between the calculated t and the t critical number. So when t equals 1.7, it gives us 5% chance of finding a mu which is our actual mean. There's only 5% chance that the mu is our actual mean. But notice that is t equals 1.7. When t equals 8, it lies on the really, really right side of this distribution, and it gives us less than 5% chance of the tested mu is our population mean, less than 5%. So that's why we will reject the null hypothesis. If our calculated t is something maybe is 1 here in the 1, so you notice that it lies in the shaded area. So that means there is more than 5% chance that the mu is our actual population mean, and we will not reject the null hypothesis.
Victor, what does P stand for when you get the calculator information?
I think that is the area on the right side of 8. It's very, very small. It's definitely smaller than 5%. In this case, I guess it's less than 1% actually.
Yeah, I got 2.3698174 e to the -8th power.
Yeah, so that is very, very small. That is the probability, the p, that is the probability of mu is our population mean. Right? And actually, intuitively, it makes sense because from the population, I find 25 samples already. This is a randomly selected 25 observations, right? And the mean is like the mean is only 0.2 something, right? And all of the sudden, I make an argument. I said, actually, the population mean is 0.338. And I would be very skeptical about that. So I do a t-test and I reject that argument.
Okay. Okay.
I'm so impressed at your collective mental enthusiasm for statistics after that midterm.
I have 0 brain cells left.
I'm listening. I'm not actively engaged. I can't.
I know this is the quietest you've ever been.
Yeah. I'm just trying to to listen and get familiar with it, but I can't write anything down. My brain's not working hard enough.
Yeah.
Good thing I subscribe to Victor on YouTube.
Yes.
Let us know when you monetize your channel, Victor. We want to share. We need some kickbacks from that monetization. But this is an MBA course after all.
Yeah.
So
okay, so for part B, do you just replace the mu 0.338 with 0.280?
Yes, that's a trial you can do now. But when you study the confidence interval during next lecture, you have a more simple way of doing that. Since you already calculated a mu equals 0.338, and actually you have a more easy way to do that. It's like the Z-score test. You remember, you can play with it's a mean plus or minus to several standard deviation. It's very impossible to get a number which is more than 3 standard deviations from the mean. I think you have some intuition about that. And when you know the confidence interval from next lecture, you can just use one formula to calculate if that mu could be another number, given that we have already tested one number. But yes, in this homework, you should just plug in 0.28 as your new tested null hypothesis and redo part A, basically.
Okay. Fine. All right, I still feel confused about identifying if it's a 2-tail test or a 1-tail test, but
okay, so we'll move on. We will move
Yeah.
on to question 2.
Okay.
This would be the part C is not very related
Yeah,
to you can't just provide some rationale and just make some sense and you get a full marks.
Okay.
So did you read the problem, the second problem?
Yeah, I read it. I can read it out loud for everyone else. Well, yeah, volunteer.
Sure.
A large potato producer in Southwest Germany obtains an average yield of 48,000 kilograms per hectare. A salesman from SKS whatever group claims its new fertilizer will increase yield by at least 5%. To test his claims, the farmer uses the new product in 16 small plots and obtains the results shown below. So how would you evaluate the salesman's claim?
The first, this is this generally asks you to do a t-test because without it you cannot argue how would you evaluate. Best way to evaluate is through a t-test.
Okay.
We can argue it without a t-test. We can just say yes or no.
Sorry?
I was making a joke. I'm sorry, Victor.
I would say no.
Oh,
So, all right. So the null hypothesis is mu is less than or equal to 50. Okay. The way I got this or attempted is if 40,000 is the average right now, but he's saying he can increase it by 5%. That gives you 50,400. Right.
Yeah, that's correct. This would be your mu, right? This is the number you want to test on.
Yeah.
And remember, every time your null hypothesis is a equation, it's not a inequality. So
Wait, say that
here,
one more time. The null hypothesis is always an equation and
yes,
not
not
a
an inequality.
inequality.
All right. So in this case, this is our null hypothesis. Mu equals what you said. It's like 5,400.
Yeah.
Yeah, mu equals 5,400. That is your null hypothesis. But what is our alternative hypothesis here?
That mu, I put that mu is greater than.
Yeah, I think that makes sense. That makes sense. Because that's something I want to achieve. Right? Like in the last, but it's tricky. I could also argue here the alternative hypothesis is mu not equals to 5,400, and then it becomes a two-tailed test. But here, I think I have a preference after reading this problem. Like I want to reject the null hypothesis maybe, but what I want more is I want my production is greater than 5,400, right? I have a preference in this situation.
so if I reject the null hypothesis, it's because it's less than 50,400. If I accept the null hypothesis, it's greater than 5,400, right?
If you accept the null hypothesis, you are accepting this argument. If you accept, and actually we don't say we accept the null hypothesis. We always say we failed to reject the null hypothesis. And in that case, it's just we failed to reject the population mean is 5,400, but many times we don't accept it because we failed to reject only because we are not as confident as 95%. But maybe I'm 80% sure that I need to reject it. But still, I failed to reject just because I'm not very confident about that. Right? But that doesn't mean I'm accepting that.
Okay, but so if you're rejecting it, if the average is not higher than 5,400, you fail to reject it if it is higher than 5,400.
Yes.
Okay.
But still, it could be a two-tailed test, right? If that's a and actually, I'm good with both, right? So you could also say the alternative. I guess actually the professor didn't require you to write the alternative hypothesis, but since it has something to do with the final alpha you are choosing, so sometimes you should think a little bit about that. So here, if my alternative hypothesis is mu not equals to 5,400, then by rejecting the null hypothesis, my claim would be the mu is either less than 5400 or larger than 5400. And the next few steps are basically very similar. It's just you need to calculate the 16 data sets, the mean of those 16 data, and the standard deviation. You're doing the same techniques, either putting that into a calculator or doing it by hand if you want. I don't do it by hand. And you use this formula again to get your calculated t-value. But in this case, the standard deviation is changing, right? And the alpha, I would still use 0.05. If you don't get any information from the question, what is your alpha, you use 0.05 because that is basically some like a default in statistics. But here the degrees of freedom is changing, and you could calculate what is the degrees of freedom and use the formula here to calculate your t-value.
Okay. So you said alpha is 0.5? No, 0.05?
0.05, yeah, it's 5%.
If it's not given default, okay.
Yeah.
Okay. Are you doing it, Olivia, or?
My brain is not functioning.
Okay, that's fine. I had really a question on 2B.
Yes.
How do you, like, I'm not sure how to proceed with how to check if they're normally distributed.
Yeah, that's a tough one. You learned the QQ plot during the class, right?
Did we learn that? I don't think so. Let me look in this PowerPoint.
I recall the statement of a QQ plot.
Yeah, but like maybe like I don't know. That felt like very much like first class, like just talking about different plots or something.
Can you guys get access to Minitab 19?
Do we have access to it? I think so. It's in the like that apps.
Yeah, you just Google Stern Apps, the first one.
Okay, hold on. Stern apps.
Because it's very difficult to plot a graph by hand. It's even more difficult actually. So and I believe you will not get a question like that during the final. But in this homework, maybe you should like use a software to solve that.
Okay. Minitab, which one? Minitab 19 or 20?
19.
All right. Yeah, it's like a 2-minute download time.
Yeah, it's annoying. I guess they just want to make sure, like after graduation, you have to pay for using the Minitab. So they don't allow you to download that. They just like give you an environment to use that.
Can you use Excel?
I don't know how to use that. I mean, in terms of statistical analysis and plotting graphs, Excel is not that strong. But I mean, maybe we could do a QQ plot on Excel, but Excel is not that powerful in terms of graphing.
My other question is, and maybe I don't want this to sound aggressive, but like, How would we know to use Minitab and a QQ plot if we didn't really go over it in like class?
Okay, so I will do that. It's the concept is very, very easy. So QQ plot is something you put in your data with a standard normal distribution, and it wants to see if your data is similar to a standard normal distribution, right? So, I mean, can you see the screen of the?
Mhm.
Okay, sure. So what I'm gonna do is first I will probably so this software generates 1,000 data for me. They are normally distributed. I just use computer program to generate 1,000 data from a normal distribution. Then I click on graph. Right, but in the homework assignment, you should probably copy paste those 16 observations in this QQ plot. In one column, there's 16 data set. And what I'm gonna do is I just click on graph. Under graph, there is one thing called the probability plot. I click on this probability plot. So that is another name for QQ plot, I think.
Okay.
The single one, okay. The graph variables is the 16 observations you plug in into the Minitab. I use 1,000 observations generated by random. Click on OK, and then there's a square here on the right down corner. It's output only. Basically, you can choose from these three modes. One is only the graph, one is both graph and your spreadsheet, and this one is only spreadsheet. So by looking at the graph, double click, I would say those 1,000 data set I generated lies on a straight line, right? And that is what the QQ plot is doing. Basically, it is comparing my data set with a standard normal distribution, right? And if they, yeah, like if they lies on a straight line, it means okay, your data set is basically normally distributed. And if it's like an S shape or some other random shapes, which is very different from the straight line, then that gives you evidence the data set you choose is not normally distributed.
Wait, so this straight line is a normal distribution?
Yeah, it is a normal distribution.
Oh, okay.
Because that's what I'm doing. I just generated 1,000 data set from a normal distribution. So when I plot that in a QQ plot, it's very straight. If you plug in those 16 observations from question 2, I guess it still lies like in the two sides of a straight line, not as beautiful as the graph here, but still we would say it's normally distributed.
Okay. What if, okay, because in my head I was thinking of the bell curve was like a normal distribution, but
yes, that is a bell. All those data are chosen from a bell curve. If you look at the data here, those data from a bell curve which has a standard deviation of 1 and the mean of 0. So you see it's basically some positive numbers, some negative numbers, not very huge, but many of them are just 0.5, 0.6 something. Those are numbers from a bell curve. And there's more number concentrating besides zeros, concentrating in the middle. And on the two tails, like it's very hard to find a number which is 3 or 4 or 5. You cannot see a 5 here, right? So basically that is a bell curve. You can see a lot of zeros here, and you cannot see a lot of 3s or 4s or 5s. This is the shape of a bell curve.
Okay. All right.
And,
I'm
and
putting in these numbers.
yeah, and in your like question 2, it's not a standard normal distribution, meaning the mean is not 0, the standard deviation is not 1, but still it has a distribution which looks very like the bell curve, but not a standard one. So, but still it's a normal distribution.
Okay. Trying to pull these in.
And the part C, the last question, I guess it's again like a profit analysis. So the cost is 700 euros. This is the cost, and the gain is 0.35 per tons. Maybe I don't know the unit. Maybe it's kg. So it's the profit is 0.35 euros per kilogram, and actually, if you have like if you fail to reject the null hypothesis and you get like your actual mean is greater than 5400, you're still making a profit, I think, because you're making like 2400 kilograms more, and that is enough to cover your cost.
Yeah.
Yeah. So
Okay.
that's how it works.
All right. I got a graph. Let's see. It's not horrible. I mean, can I just show you and like?
Yeah, definitely. Yeah, I would say you notice there's 3 red lines, right? The one in the middle is straight line. That is the approximation of how those data points lies in it. And there's one on the right, one on the left, and all your data point is inside those 2 boundaries.
Okay.
So I would say basically generating a straight line. Yes, and it's normally distributed.
Okay. If it was like outside of the boundary, it wouldn't be.
Yeah, yeah. So
Okay.
maybe I would say it's not a very normally distributed. There's some outliers, maybe some outliers, or maybe that's a normal distribution with some outliers, and maybe it is not a normal distribution.
Okay.
Yeah.
Can I just how do I say that on the homework, like the written homework to you?
You just say like, oh, maybe you can copy that graph in your like a PDF file or something.
Okay.
That is enough. Yeah.
Okay. Got it. All right. This is not easy, but okay.
Yeah, it's not easy.
Yeah. Oh my god.
You have already like go into like statistical tasks, and after that you will know regression analysis, and that's everything during this semester.
Okay.
It's pretty tough. I mean, when I took this class, I with the same materials, but I was having 3 classes every week,
Well,
75 minutes per class. So actually, we are like learning. We have more learning time with the same materials. So like I think it's easier for me to learn those materials. But for MBA class, like it's more intense.
yes.
Work extremely hard to catch all the materials.
Yes. Yeah. Yeah. Okay. Well, thank you. Olivia, do you have anything else?
Not for now.
Yeah,
I think on this homework.
Yeah, it wasn't easy at all.
I will like post the recordings on the YouTube channel, and yeah, you could tell other students to watch it, because like yesterday, I also had an office hour, but somehow I showed the answer of the question. I just click on my PDF and I showed the answer, and it's inside the recordings. So I think it's not very good to post.
You can't post it.
Yeah, yeah.
OMG! TFT to that one.
Oh well, they can't rewatch it though. Okay. All right. Thank you, Victor. Have a good
I
night.
think in that case maybe I will be fired. So
Oh my God.
yeah,
No, you can't get fired. You're the only one that tells us what to do.
sure. So have a good night, and if you have any questions, just send me an email.
Okay.
Sure.
Bye.
Bye.
Bye.